So last time we finished the most classical part of Turan, the dense case, meaning that the forbidden graph is a non-bipartite graph. By Ehrlich-Schimonovich theorem, we know that when you forbid a non-bipartite graph, your graph can still be dense with positive edge density. And we gave a remark that, so here, let me write it. So Ehrlich-Schimonovich says that the extremal number of a graph is governed by its chromatic number. Okay. I don't remember which it's almost the same. So, but the thing is, when chi of h, when the forbidden graph has chromatic number 2, bipartite, we only get a little o of n squared bound. So today we will see actually for any bipartite graph, we should get a much stronger bound, a polynomial improvement, h. We will get big O of n to the 2 minus some constant that depends on h. So asymptotically, we win by a power of n here compared to the n squared. So what are the two most common bipartite graphs? I would say that, so today we're going to talk about bipartite two-round problem, bipartite. Sometimes people also call it degenerate problem, degenerate two-round problem, referring to the fact that our bound is subquadratic. So the most common one, most basic bipartite graphs, there are two family. One is analogy of complete graph. We have complete bipartite graph. So you have, say, S vertices here, you have T vertices here, you have everything in between. The complete bipartite graph, which we will use KST to denote. And another family is the even cycle. So we have 4 cycle, 6 cycle, 8 cycle, so on and so forth. We will use C2L to denote the even cycle, where 2L is both the number of vertices and the number of edges. We start with the simplest possible bipartite graph, which is this guy, the 4 cycle. And 4 cycle actually is also a complete bipartite graph. You can think of a 4 cycle as a complete bipartite graph with 2 vertices on each side, right? So 4 cycle is also K22 that look like this. So the proof that we will see to give an improvement, we know that by ESS, 4 cycle has extreme number little o of n squared. So to improve it, rather than viewing it as a cycle, let's view it as a complete bipartite graph, which is going to be useful perspective in our double counting strategy. So before I start this bipartite two-round part, let me just mention a nice survey by, so here, if you want to know more about bipartite two-round, there's a nice survey by Fiorelli and Shimonovich. It's called degenerate bipartite Turan. You can Google it. So this C4 problem is perhaps one of the earliest bipartite Turan result by Erdős. We have this theorem that we want to prove, saying that the extremal number of n C4 is at most this number. Let me write it down. N over 4, 1 plus square root of 4n minus 3. So it's a rather specific number function. Let's look at its asymptotic behavior. This number is roughly, let's see, 1 is really small compared to square root n. We just think of n going to infinity. So forget about 1 here. And this 3 minus 3 is also a constant term. So this is the main guy, which is roughly 2 square root n. So this times that, the asymptotic of this is 1/2 times n to the 3/2. So this is 1/2 plus little o1 times n to the 3/2. This is the first improvement we will see of ESS from little o of n squared to n to the 3/2. And later, in fact, we will see that this n to the 3/2 is the correct exponent, 3/2, and also this leading constant 1/2 is asymptotically best possible. Okay, so later we will see that in fact we have a construction showing that we have equality. How do we do the upper bound? So here, the idea is very simple. Viewing full cycle as a complete bipartite graph with 2 vertices on each side, we're going to do double counting on this path of length 2 on 3 vertices, which we also call cherry. It looks like a cherry, right? How do you draw a cherry? Something like this. Looks like a cherry. So we count cherry, and the trick is that we cannot have 2 cherries sharing the common endpoint. Because you have 2 sharing the endpoints, you will get a full cycle. That's the idea. Double counting. So proof, maybe let me first say the idea. This one line, double counting cherries, which is K1, 2. Here's the detail. So let G be an M vertex C4 free graph. Okay, how do we, let's first count the number of cherries. Okay, so the number of cherries equals to, how do we count it? One way of counting it is to start with its midpoint. Okay, so we start with a midpoint V. Think of the V here. Look at its neighborhood. And all we need to do now is just to pick 2 vertices here. We'll get our cherry. Okay, so meaning that, let me write it down. We have a midpoint V, first step, second step, Pick two neighbors. Okay. So that tells us that the number of cherries ranging over all vertices in my graph from its neighbors, which there are d of b many, I'm choosing 2. Now we're going to use a standard convexity inequality, Jensen's inequality. So let's briefly recall. I probably have used it before without actually. So what's Jensen's inequality? Jensen's inequality is saying if you have a function f that's convex, okay, and for any random variable x, how do we compare the expectation of f of x versus if you switch these two operations, first take expectation, then take f. How do we compare these two? Well, the easiest way is to remember this picture. We have this convex function f curving upwards. Now, what is this guy? Expectation of fx. So if I have these two value, let's say x takes two values here, then their expectation is exactly here in the middle, right? This is my expectation of fx. And what about the other way around? This guy, what's the expectation of x? So if x takes these two values, ex is here. If you take the value, we have greater than here. Okay. Now, using this inequality with this is greater than, we use Jensen, where the f you think of is x choose 2, this function inside. We get that this summation is minimized when all the degrees are the same. So equals to, you have n vertices times all the degrees are the same, means you sum up all the degrees divided by n should be average degree here. Choose 2. Okay, then this is by handshaking lemma. Sum of degree is 2 times the number of edges. Choose 2, simplifying it, we get 2 e of g squared over n minus e of g. Okay, so that's one way of bounding cherry from below. Another way is, as I mentioned, we cannot have two cherries sharing the same ends. We would have getting a C4. So on the other hand, no two cherries share endpoints. Otherwise, we get C4, a contradiction. So that means the number of cherries is at most n choose 2, because the number of cherries is at most the number of endpoints, which cannot be shared. So the number of endpoints is the number of cherries. And we have a lower bound here, we have an upper bound here, compare, you get the answer. I will not do the calculation. Any question? Okay, now here's an exercise for you. Well, after seeing this proof, I wouldn't call it exercise, more like reviewing the checking if you understand the argument. So try to prove that for complete bipartite graphs, we can use similar arguments to show that this is at most t times n to the 2 minus 1 over s. Again, for complete bipartite graphs, we gain the power of n. So it's enough to prove this weaker exercise. We know the power here. A more careful calculation will give this theorem, which perhaps many of you have seen it before, the Kovály-Sós-Turán. Theorem says for every s less than t, you have almost the same, but with a slightly improved leading constants. It's at most 1/2 plus little 1 times t minus 1, 1 over s, n to the 2 minus 1 over s. So I will not do this calculation. Try to do this exercise yourself. Now you see this simple double counting arguments already tell us what we're claiming before. So what do we claim? We claim that for any bipartite graphs, we can get the power saving from quadratic bound. And that's simply a consequence of Kovály-Sós-Turán. Because every bipartite graph, it's a subgraph of some large enough KST. So we improve this. One of the major open problem is how is this power correct? N to the 2 minus 1 over s. So maybe I should use red color. Major open problem is lower bound. To obtain lower bound. So what we know is that we have a matching lower bound. So if you don't care about the constant up front, look at the behavior of the main term as a function of n, we can get the same power if only in the case s equal to 2, 3, and when t is very skewed. T is much larger than s. Before it was factorial. Before it's factorial by Kovály, Ronnie Sabor, and along. And recently, fairly recently, maybe 2 years ago, 3 years ago, Boris' book improved it to something slightly below exponential, like roughly exponential of s. So something like this, okay? Now, so as you see, even when s equal to 4, it's open. I think the best bound for K for 4, as I said, upper bound is n to the 7 over 4, 2 minus 1 over 4. And lower bound, we have nothing better than the tight lower bound for K33 free graph. Right? Let's see an application. Why Erdős at the first place consider C4 free graphs, extremal number of it. It was because of an application. He started off not doing bipartite Turing problems exactly. So he was doing a number theory problem involving a notion called sit-down sets. So here, definition, C4 free graphs and sit-down sets. So a set has, let's say, k elements. Natural number is a sit-down set if all pairwise sums AI plus AJ are distinct. In other words, A plus B equal to C plus D has no non-trivial solution, only trivial solution. What's the trivial solution? The two numbers on the left are the same two numbers on the right as a set. Yes. Okay. What would be a simple example of sit-down sets? Here's an easy example. You might immediately come into your mind. So, okay, let's start with a question. Let me see. So the question is, how large a sit-down set can a sit-down set consisting of taking elements from the first n integers be? How large can it be? Well, here's an example. If it's only taking integers from first n, we can take powers of 2 trivially. So A1 is 1, 2, 2 squared, da, da, da. Let's say n is a power of 2, why not? But the size is only logarithmic in n. It's very small. So it turns out we can get as large as not just polynomial in n, all the way to square root n size. So this is a known theorem, which we will not prove here. So the largest sit-down sets in n has size we even know asymptotically. Up to the little o1, this is best possible square root n size. Okay. So later, I'll give you some exercise. You will see yourself that, oh no, it's the other way. So, okay, so here's the exercise. What does it mean largest sit-down set has size asymptotically square root n? That means, first of all, every sit-down set has size at most this size. Second of all, you need to give a construction, matching lower bound construction. So the first exercise is to prove an upper bound, which is slightly weaker. It's fairly simple exercise. So prove the weaker upper bound that for any C-down set in N has size m less than 2 square root n. Up to a factor of 2 is very easy to prove. Okay. The second exercise is, we know that there is a construction of C-down sets of size square root n. We don't know how it look like, but use that C-down set, large one, as black box to construct the C4 free graph with n to the 3/2 number of edges. Use the theorem above to construct C4 free graphs with say m vertex C4 free graphs with n to the 3/2 edges. So we've seen this upper bound before. Up to the constant, this will determine the order of magnitude for extremal number of C4. Now let's actually construct C4 free graphs and asymptotically extremal C4 free graphs without using the C-down set. Let's do it directly. This is a geometric construction using the fact that if you take any two lines, two straight lines can only intersect at one point. So let's see how we use this simple fact to construct some dense C4 free graphs. This is a theorem of construction of Erdős, Rényi, Sós. The extremal number of C4 is at least, we have proved this as a topic before, as upper bound, as to lower bound. We're going to take lines and points in the finite field setting. So, for large enough n, basic number theory says that we can always find a prime. There's a prime number P between 1 minus theta of 1 square root n plus 1 and 1 and square root n plus 1. So just take a prime that's very close to n plus 1. Now we're going to consider the following graph. So what's our graph? V of G is Fp squared, but with the origin removed. So elements are paired of elements in Fp. So remove 0, 0. The rest are the vertices. How are we going to build an edge? Well, we should think of, so here's how we build an edge. E of G, you have two vertices, AB in Fp squared, adjacent to another vertex, which I write xy. So this just means they are adjacent in G. Or to be precise, I should use this symbol, but it's clear that we're talking about G here. If and only if they satisfy this equation. So what is this guy? This is a line, okay? One way of remembering this construction is that we have a vertices here. You can consider it as a point in here. You can also consider it as a line with these two parameters. So a line is adjacent to a point if and only if this point lies on this line. That means they satisfy this equation. Okay, so this you can think of it as a line, sort of. This you can think of it as a point, and they are adjacent when, if and only if, the point is on the line. This is what it means here. Okay, maybe sometimes there's loop, meaning what? Maybe AB is adjacent to AB, A squared plus B squared is 1. If there's a loop, delete the loop. It's not going to affect asymptotic value on the size of G. So we need to prove two things. One is that what's the number of edges? It should be something like this. And second of all is C4 free. So let's first consider the size. The size is easy. Every vertex in G has degree P or P minus 1. Why? If you, let's say, fix AB, then the number of solutions, well, if you further fix X, then there are P choices to choose Y so that, oh, sorry. You first fix the vertex AB, okay? Now, you have P choices to choose X. After you choose X, Y is uniquely determined. You solve this. So there's P choices, maybe P minus 1 if there's a loop. So we have the number of edges is at least, well, every guy has degree at least P minus 1. The number of vertices is P squared minus 1. We have 0, 0 removed. Handshaking lemma divided by 2. So we have this equals to 1/2 minus theta over 1 and to the 3/2. We have the right asymptotic on the size. Why there's no two lines C4? Well, as I said, if you have two, this just means that the AB line, you have X, Y line points lies on the AB line. Okay, if you have two A prime, B prime, and two lines can only have one intersection. That's the reason. Take two distinct vertices. Let's say AI, BI. I is either 1 or 2. What's N AI, BI? What's the neighborhood of this vertex? Is consist of all vertices X, Y satisfying AIX plus BIY equal to 1, which is a line in FP squared. Okay, as A1, B1 and A2, B2, we're starting with two different points. The corresponding line are two different lines. Okay, and A1, B1 and N A2, B2 are two different lines. Which and intersect at most one point, which is the same as saying A1, B1, A2, B2 have at most one common neighbor. Okay. So maybe let me mention an open problem involving C4 here. So this open, some variation of this extremal problem on C4. If you have a three-part graph, G on m by m vertices, that means you have three parts, each part m vertices, all the edges going in between. Let's say your parts are V1, V2, V3. So if I tell you that V1, V2, V2, V3, V1, V3, these three pairs, each pair is C4 free, C4 free, C4 free. This is C4 free, all parallel. What's the maximum number of triangles? Such graph. How many triangles can such graph have? All right. The best known bound up to constants n to the 7/4. This is just by Cauchy-Schwarz. Apply it twice in a clever way, not so hard. And lower bound construction, the best known is n to the 5/3. Okay. Closing this gap, I think, will be interesting. This is the result of Kutter, Matthews, Emmons. Okay, so let's see a quick application of bipartite Turan problem. So we know before, remember KST says that if you forbid KST, then the number of edges is n to the 2 minus 1 over s. Let's say s is less than t. Here's a geometric application to the quick application to Erdős unit distance problem. So what is this problem? Well, here's the problem. I would say it's a proposition, a set of m points in the plane R2 determines at most some constant times n to the 3/2 unit distance. Okay, how do we do that? Well, proof. We need to show that no matter how we have m points arrangements in the plane, so this is my arrangement. All right, m points. Then we cannot have much more than n to the 3/2 many pairs between which the distance is 1. The trick is to build an auxiliary graph G on these m points. So start with the arbitrary m points arrangement, build on this a graph where 2 points adjacent when their distance is 1, exactly the unit distance. If distance between them is 1. So here, for example, you have these two, distance 1, so they're adjacent. All right. The key observation, so to give an upper bound on the number of pairs at unit distance apart is basically to give an upper bound on the number of edges. So we need to give an upper bound, we need to upper bound E of G. The trick is, the idea is that this graph G observation is K2, 3 free. Why? What's K2, 3? You don't have two vertices x, y sharing 3 neighbors. So if you have a point x, what's its neighbor? So its neighbor is something like this, right? Let me draw. Are all points that are distance 1 from it. Okay. This is distance 1. So all its neighbor lies on this blue circle. And you have another point, let's say y, this is x. All its neighbor lies on the blue, on this red cycle. Okay, we'll try. Slightly better. It lies on this red cycle. So 2 cycles can only intersect at 2 points. Okay. I will not write the details. It's clear from the picture. So the result follows from KST. KST says if you K2, 3 free, your bound is n to the 2 minus 1/2. This bound is not tight, meaning that we can improve it. The best bound so far upper bound is n to the 4/3 by Semerady and Trotter. improving this 4/3 exponent is it's very important problem. So I want to finish the complete bipartite graph parts by telling you the tight construction for K3 free graphs. So remember, let's recall, here. For KST, remember, we have tight construction for K22, which is C4 free, and K3 free graph. All right. As for when it's very skewed, maybe in the later advanced part, we're going to mention these other constructions. One classical one by them is so-called norm graph, and the recent development is random algebraic construction of Horace-Poe. Okay, so what is this tight K3 construction? Brown's construction. Matching lower bound. Remember, KST give also enter the 5/3 as upper bound. The idea is, again, geometric. The idea is 3 spheres in R3 intuition have at most 2 points in common. Okay, this should be clear, this intuition, because you have one, you have another one, then their intersection is again a sphere, but 1 dimension lower. So it's a cycle. Now you have a third sphere going across. So this is the first one, second one, and you have the third one. What color? Purple. Going through, you only intersect at these 2 points. Okay. How do we make use of this fact? We're gonna let, here's the construction. The vertex set is FP3. 2 vertices, you have A, B, C, adjacent to A prime, B prime, C prime, when the distance from them, between them is 1. When, if and only if A minus A prime squared, what's their distance? You take the difference of the coordinates, square, sum them up, equals to 1. So, in this way, if you have a vertex ABC, what are all the neighbors A prime, B prime, C prime? It has to satisfy this equation, which is exactly the sphere with ABC as the center. All the points on the sphere are its neighbor. So if you have 3 points, 1, 2, 3, their common neighbor are exactly the common intersection of 3 spheres, which has at most 2 points. So in this way, the neighborhood of a vertex corresponds to a sphere around V, and you have that. I will skip the details. You can check easily that it has this many edges. So that's all I want to say about complete bipartite graphs at the moment. Let's move on to the second most common bipartite graphs, the even cycle. Well, C4 is even cycle, but let's look at longer even cycles. What do we know about them? The extremal number. Intuitively, complete bipartite graphs, look at the KST. Complete bipartite graphs intuitively are the largest bipartite graph. They are densest given the set of vertices. An even cycle is much sparser. You only have n vertices and two L vertices, two L edges, much sparser than KST, which means that it's easier to find them as subgraphs in the given graph, meaning that we should obtain a better upper bound than what we've seen here. This is a classical result of Boundy and Shimonovich in the 80s, who proved that the extremal number of C2K is big O of n to the 1 plus 1 over k. Okay, what's hidden here is some constant, which in their proof depends on k. All right. Well, okay. A quick remark is, again, what's the first thing that should come into our mind is this upper bound height. Is this exponent 1 plus 1 over k the right exponent? The answer is yes, when k equal to 2, 3, 5, only these three values. So the only matching lower bound known is when k equal to 2. We've seen k equal to 2. N to the 3 half is C4. We also have for 6 cycle and 10 cycles. That's the only thing we know, which comes from this finite geometry, polarity graphs. I will not talk about these lower bound constructions here. Let's see the upper bound proof. Let's try to prove this n to the 1 plus 1 over k. There are a couple of ways to establish this upper bound. The most classical way is through this BFS search. Okay. So maybe the simplest open case, as you see, there's no 4 here. So we don't know what's the exponent of extremal number of C8. For example, for C8, we have n to the 5 over 4. I believe the best is n to the 6 over 5. And this is by this group of people. So we will see a proof of this bounded Shumanovich result with the specific quantitative constants by Pickerquote. Actually, I will only present the sketch of this proof for large n. the extremal number of C2K is at most 4K times n to the 1 plus 1 over K. So we have an explicit constant here. And so far, the best leading constant here in the front is something like square root n. Best leading constant as a function of K is something like K square root K, log K maybe. A student from CMU. So it is remarked that there's a natural barrier in this BFS search type argument. We will get stuck at square root K. So going beyond square root K could be interesting. Although some people actually believe that it should be little o of 1 plus n to the 1 plus 1 over K. So this guy shouldn't even be there, some people believe. Okay, so what is BFS? Some of you might have seen it, some of you might not. So let's first see what is this BFS thing. BFS is it's short for breadth first search. Okay, by the name, it's an exploration algorithm of a graph where we're going to output the tree, spanning tree, including all vertices of the graph. And this exploring algorithm will prioritize breadth. Okay, what does it mean? I will just do it from an example. So it's an exploration algorithm. It's a graph exploration algorithm outputting output is a spanning tree. Here's a example. Suppose we have a graph. I think this is complicated enough. So we add one more edge. Let's do this edge. Yeah, why not? Let's add a pendant edge. All right, so this is our G. What does BFS do? Anyone give us a graph like this one here? We're going to output a spanning tree. Spanning means a subgraph, which is a tree of the original graph on all vertices. Okay. So we're going to start with the arbitrary vertex. Let's say we start with the arbitrary vertex 1. How does exploration goes? Basically, the idea is the idea is we start with arbitrary vertex. You're going to explore all its neighbors. So this is what it means, breadth. Okay, explore all its neighbor. When you exhaust all its neighbor, now you go to the first neighbor of it. You start exhausting all the first child's neighbor. When it's done, you go back here, exhaust everything here. When you go back here, you exhaust everything here, here, here. In other words, you start with arbitrary vertex. You find all the vertices of distance 1 from it. That's the first layer, children. Then you find all the vertices that's of distance 2 from it. That's like the grandchildren. After you finish all the grandchildren, then you go to the grandchildren, the third layer. That's the BFS. Okay, let me draw this picture here. It just means that you start with a vertex, you output the tree where you prioritize the vertices that's closest to you. So here, let's do this. Example, from 1, let's go to one of its children, distance 1. You can do any one. Let's do this one, say. So this is the second vertex. Let's use purple, green, purple. So you go here. Then we don't continue from 2, vertex 2. Remember, we have to finish all descendant of children of 1. So you can go here, for example, and then you go here. After you go finish the third one, there's no children of 1 that we've never seen. So this is 2, 3, 4th vertex. Now you're going to continue from vertex 2. You go to the first children, which is 2 here, and see, okay, what about his children? But all his children is the one that we've already seen. So we don't do anything for 2. We move on to the next one, which is 3, which is here. Okay, one of his children is 4. We've seen it before. Don't do anything. We explore all these ones, right? So second layer, let me use a different color. Oops. Okay, you explore in any order. That's the second layer. So this is 5, 6, and continue one more round. Let's do this red. I'm not done with the second. Now you move to 4, vertex 4, right? 4 should go also explore this vertex. This is vertex number 7, which is at the third layer. So 1, 2, 3, 4, 5, 6, 7, and you explore from 5. Explore this is 8, 9. 8, there's only 1 here. 9, there's 1 here. Something like this. So how do we prove an upper bound on the extremal number of even cycles using BFS search? Let's do an easier one. Let's say let's try to prove an easier one. Let's let C, the curly C2K, to denote all even cycles of length up to 2K. So C4, C6, C8, C2K, okay? Let's try to prove, if you look at the extremal number of this finite family, we can prove n to the 1 plus 1 over k, the exponent that we want. Here, the difference is, the original problem, we only forbid one graph. Here, we, instead of forbidding C2K, we also forbid all the shorter even cycles. And it turns out that when we allow to forbid all the shorter even cycles, the proof is very, very simple. So using BFS, here's the proof. Take a BFS search, you get a tree, right? You get a spanning tree T. Let's say the root is X. You have all its neighbors of X here. All right. Now, the idea is now you finish the first layer exploration. The second layer exploration, the neighbor, they are again pairwise disjoint. Because if you have two intersect, you will get a full cycle. You can go back and build a full cycle. Okay, so this must be disjoint. Similarly, if you go to the third layer, if you go down, this is again disjoint. These two. Otherwise, you will get a sixth cycle. You go back, or maybe you already go back like this. That's full cycle. Maybe you go back like this all the way to X, you get a sixth cycle. So that means you can, each layer is getting larger and larger because these are all disjoints. All right. So what do we have? We have C2K3 implies each layer, let's say V1, V2, . Each layer Vi for I less than K is greater than the minimum degree of the graph raised to power I, right? The first layer is at least minimum degree. The second layer, all these vertices expand by another factor of delta G, so square. Third layer, so on and so forth. Up to K's layer, you can always maintain this disjointness. Otherwise, you chase back, you get a cycle, one of the short cycles in here. So what we have is, at the end, you have Vk, which is at least delta G to the K, which is at most everything, total number of vertices in your graph. What do we get? We get delta G is at most n to the 1 over K. There is a simple proposition saying that you can always pass to a subgraph where the minimum degree is at least half of the average degree. So minimum degree and average degree, if you don't care about constant factor on the number of edges, are the same. So this is also saying average degree is at most roughly this much. So the total number of edges on n vertices, you just plus 1 here. That's the bound. It will be all shorter cycles. An important remark here is that this already indicates where the difficult part of the bipartite Turan problem is, that it's easy to forbid the graph that we want, and these are the homomorphic image of, you can think of this as a homomorphic image of even cycle C2K. You can easily find the homomorphism from a longer cycle to a shorter cycle, okay? And these are degenerate homomorphism, meaning that it's not injective. So controlling the number of degenerate homomorphisms of the bipartite graph we want is the key difficulty in dealing with bipartite Turan problems. So this is the remark I want to make. To prove to forbid only C2K, we need to be more careful. Note that shorter even cycles are homomorphic image of C2K. So we need to be careful to not finding just a homomorphic image of C2K is not enough. So we need to exclude them. The main difficulty in many bipartite Turing problem is to control the count of such degenerate homomorphisms. So let me convince you how we can turn this idea of BFS into a proof forbidding just the 2K cycle, not the shorter ones. We need some basic proposition. Every graph G contains a subgraph H where the mean degree is at least average degree G over 2. That's the one that I mentioned. And also every graph contains a bipartite subgraph H with at least half of the edges of G. Okay. Combining these two by losing a factor of we may focus, we may assume our host graph G is bipartite and mean degree is at least if your entropy is D, you can pass the subgraph with D over 2 average. Yes. Okay. What I'm saying is correct, but probably it doesn't go directly from here. Wait, let me erase these comments. I will let you know how to use it later. What I wrote on was still correct, but okay, so how can we be careful and remember here in this argument, the key part is we want to prove that each VI is expanding fast. And at the end, we have the last layer, which is expanding like minimum degree or average degree to the power k, which is at most the total number of vertices, to conclude on the upper bound on average degree. We want to do the same here. We want to control the growth of each layer when you do the BFS from the graph, and you want to show that still every layer expands roughly by this factor. But the problem here is that before finding even a shorter cycle, we will reach a contradiction. Here, we have to find exactly cycle of length 2k. Okay? The nice idea was that was already appeared in Bondi and Schumler's paper in the 80s, is to use this so-called this theta graph. So what is this definition of theta graph? A theta k graph is a cycle, is a graph, which is a cycle of length at least 2k with a chord. Okay, just look like you have a cycle of a length at least 2k, and there is some chord. Let me use a different color. At least one chord. You could have more. That's still theta k graph. Exercise. Prove that, it's not hard to prove. Prove that for every k at least 3, if you have a graph H that's bipartite graph with average degree at least 2k, then H contains a theta k graph. Right? Whenever a bipartite graph has average value at least 2k, we will find theta k as a subgraph. So why is this useful? The idea is the following. We consider this BFS search tree, a BSF tree, starting from some vertex. You go several layers. Let's say at the end, you exhaust all the vertices, look something like this. The idea is that between any of the first k layers, pairs of, oops. So if between any two layers here, if you have this theta graph with a chord, then we can somehow make use of this theta graph with a chord to find the C2K. Same with any two layer, okay? If you have this theta graph that looks like this, right? The even cycle with a chord. So let's add one more chord. This is your theta graph. With a chord, this is your theta K. Then somehow we can make use of it to trace back, maybe meeting here to find an even cycle. Maybe you go all the way back to the root. I don't know, you go somewhere and then we will use this theta K to find the C2K. What that will require is that, okay, let's first see what this implies. But we also know by the exercise above that when you have just constant average degree, you already contains a theta K as a subgraph. And we know that between any two consecutive layers, you cannot have a theta K as subgraph. Otherwise, we can use this theta graph to cleverly find the C2K. So that means between layers, there are very few edges by the exercise. So by the exercise, we know that between layers, few edges. But every vertex has a mean degree. If there are few edges, that means it sends most of the edges downwards. It sends few edges upwards, right? That's also saying that these layers are expanding. Every vertex sends most edges downward. Means layers are expanding. Again, by a factor of the average degree of the graph. Okay. So after k layers, the kth layer, vk, which is average degree to the k less than n, implies that average degree is again at most n to the 1 plus 1 over k. So this is how we can use this theta k graph, saying that we still have this expanding property of the layers. Now, to make this possible, we need a lemma which says that if you have a theta k graph between layers, we can actually find many paths with different lengths. If theta k is very rich at paths, so many distinct lengths, then intuitively we can use these paths of distinct length and then use the path back on this tree to complete the cycle of length 2k. This is the contents of this lemma, which we will not prove, but it's a useful lemma to remember. So for this, to this end, we use theta k for building C2k, we will need to find many paths of varying length in theta k, which is this lemma. The proof of lemma is not long, but it's not trivial. Let f be a theta k graph on vertex sets. Oh, no, sorry. You have a theta k graph f, and let A union B be a partition, non-trivial partition of VF. Here, non-trivial just means none of them is empty set. You cannot put everything into one set. The conclusion is that, so you have this theta graph, you have some partition A and B, okay, A and B, and you have theta graph lying somewhere here. I don't know how it looks like. This is your theta graph. Then the conclusion is, if f is not bipartite with bipartition A union B, then there exists AB path of all lengths less than the number of vertices in F. Let's say it's N. All right. So what does this say? Suppose this is A, this is B. All he's saying that is that, okay, you have a theta k graph here, and you have some you have some partition. As long as it's not the case that this graph, theta graph, is bipartite, and it happens that AB is a bipartition of this. If this is not the case, then we can always find AB path means a path starting with A and ending in B, such that to realize all length strictly less than the total number of vertices in the theta k graph. So you can find many, many paths of different lengths between A and B. Okay, that's all I want to say about the BFS proof for even cycles. The full proof you can see in Oleg Pikriko's paper, not so long, but let me repeat the idea one more time. First of all, one of the key ideas is to make use of this structure called theta k graph, which is nothing but you have a long cycle with at least one chord. And this lemma is saying that given a theta k graph, you can find many, many different length paths in there, in this theta k graph. You can find all the paths of length up to almost spanning path. Then, how we're going to use this is that this theta graph is very easy to find in the graph. So as long as any bipartite graph, its average degree is at least 2k, where k is constants, nothing to do with n, then already you can find such a theta k graph. Okay, putting everything together, we again do this BFS search. You start with the vertex in your graph, find all the vertices of distance 1 from it, find all the vertices of distance 2 from it, distance 3, so on and so forth, exhaust all the vertices. The observation now is that between any consecutive layers, let's say this graph is bipartite, so there's no edges inside here, right? So between any two layers, consecutive, we shouldn't have theta k there. If you ever have a theta k, like this blue one there, using this lemma, that it's very rich in paths of different length, then we can use these many paths of different lengths together with this tree structure you trace back cleverly to close this path into a cycle of the desired length 2k. So between two consecutive layers, no theta k. If there's no theta k, that means your average degree should be less than 2k, less than the constant. We have minimum degree condition. If it's very sparse, you see, from this layer, it sends everything downwards, apart from one edge up. So, but it's very sparse. That can only means that this set must be large. And all the vertices here sends most of its neighbors down, very few up, to be able to make this pair sparse without having theta k. So every layer is expanding. Again, finishing the proof. Any question? I choose to only present this sketch of the proof is because now there's more modern proof using homomorphism inequalities we will see later. Producing slightly weaker quantitative bounds, but I think it's much cleaner proof than this combinatorial proof. But still, it's good to know this BFS argument through this sketch.